think we're ready to take on the incline plane. Here we have a box sitting at rest on an inclined surface. Go ahead and draw a free body diagram for that box. If this is my box on the incline, I know the force of gravity is reaching in and pulling toward the center of the earth, and the only thing that's touching the box is the surface. And this box isn't going anywhere, so the surface must be pushing up on the box with the force equal and opposite to the force of gravity. Is that what you drew? I bet it isn't, because for some reason we like to break up the interaction that objects have with surfaces into two forces. A normal force that's normal to the surface or perpendicular to the surface, and a friction force that acts parallel to the surface. So you probably drew something that looked more like this. Here we have our normal force, our static friction force pointing up the hill. How do we know it's pointing up the hill? Because the box isn't moving. And gravity would want it to go down the hill. And the force of gravity. Now, once we have this drawing, I usually start out by just drawing each vector just as I see it. The force of gravity points toward the center of the earth. If I had some other force pointing in some weird direction, I would just draw it exactly the way I see it. Once I have this free body diagram with the actual forces, then I say to myself, what coordinate system is appropriate for this problem? Usually I want to pick the direction of my acceleration to be one of my directions. This box isn't going anywhere, but if it was to go somewhere, if it was to move, how would it move? It would probably move along the surface of the incline, up or down the surface of the incline. So I would pick my coordinate system to match that. We could call this one direction and perpendicular to it the other direction. You can call them x and y. You can call them parallel and perpendicular, parallel to the acceleration if there is some, and perpendicular to the acceleration, whatever you like. So now I can split this up into its components. The normal force and the friction force are already in this coordinate system. I don't have to break them up into components. But my force of gravity needs to be broken into components to get it into this nice coordinate system. So it has a component parallel to the surface and a component perpendicular to the surface. And let's take a look at what those are. If we zoom in on our drawing of the box on the incline, we know the force of gravity acts toward the center of the earth. Since we know that this is a 90-degree angle, this angle up here is going to be 90 minus theta, the angle of our incline. We want to break up the force of gravity into two other vectors. One that's perpendicular to the surface and one that's parallel to the surface. So these two form a right angle. The red one we're calling F perpendicular, and the blue one F parallel. So how do we find those components? Well, if the red vector is perpendicular to the surface, then this is a 90-degree angle. That means that we've got 90 degrees over here. We've got 90 minus theta on the other side, and what does that leave? Theta for in between. That means that my red side here, F sub g perpendicular, is going to be F sub g times the cosine of theta, and F sub g parallel is going to be F sub g times the sine of theta. F sub g parallel is F sub g sine theta because it's the opposite side from theta. We use the sine. And F sub g perpendicular is the adjacent side, so we use cosine. So if I apply Newton's second law, sum of the forces equals ma. This is a vector addition equation, and I can split it up into components. Sum of the forces in the parallel direction have to equal ma in the parallel direction, and sum of the forces in the perpendicular direction will equal ma perpendicular. And in this case, the box is not moving. It's not jumping up off the incline or falling down through the incline. So this is 0, a perpendicular 0. And it's not moving along the incline either. So I know a parallel is also 0 in this case. And I pick a direction as positive. I can pick up the incline as my positive direction. So in other words, I'll use green highlighter here for my positive direction. This is my positive direction. That means I have F sub s in the positive direction, F sub g parallel in the negative direction, and those two have to add up to be 0 since my acceleration is 0. And I know F sub g parallel is mg sine theta. We can do the same in the perpendicular direction. Pick a positive direction. I'll use blue highlighter to indicate my positive direction is this way. So I have two forces. In the positive direction, I have my normal force. In the negative direction, I have Fg perpendicular. And those have to add up to be ma, which in this case is 0. And I know Fg perpendicular. Just to recap, start out by drawing a free body diagram with the force vectors representing the exact forces. Don't worry about components yet. Then pick a coordinate system that makes sense and use components that are all in that coordinate system. Don't put both vectors down. Don't put F sub g and the components in the same free body diagram. That would indicate you have too many forces. You have two forces of gravity acting on your object. You either indicate it with the force for the force of gravity, or the two components. Don't put both in the same free body diagram.